Hey everyone, welcome back to the RC F-16 project. In today's video, we'll take a short break from the build and talk about weight and balance. For the purposes of this video, the weight I'll be calculating is the total weight of the airplane ready to fly, and when I talk about balance, I'm referring to the longitudinal location of the airplane's center of gravity. When designing an airplane from scratch, it's really important to know how heavy the airplane will end up being, and also where its center of gravity will be located. Regarding weight, if the plane is too heavy, it'll make the plane feel underpowered, result in a very slow climb rate, and also require the airplane to have a higher airspeed to generate enough lift to keep the airplane in the air, among other effects on flight performance. Arguably more important than the weight is the location of the center of gravity along the length of the fuselage, since this affects the airplane's stability. If the CG is too far back, the airplane will be statically unstable, making pitch control extremely difficult by hand, because the airplane will constantly want to pitch up or pitch down. If the CG is too far forward, the airplane will be statically stable, but too stable, making it so the horizontal stabilizer does not have enough pitch authority to keep the nose of the airplane up. For an RC airplane, you want the CG to be at a good spot that provides enough static stability, yet good maneuverability. Before I started the build, I made a spreadsheet that estimates the plane's total weight and longitudinal CG location. This was extremely valuable because it helped validate that my planned build technique and material choices wouldn't result in the plane being too heavy, and it also helped me position the EDF and battery. I wanted to avoid adding nose or tail weights to adjust the CG location, but instead locate the heaviest components in spots that naturally bring the CG where I want it. The EDF and battery are the two heaviest electrical components of the plane, and therefore will have a large impact on the airplane's CG. Using this spreadsheet, I was able to easily play around with different battery and EDF locations until the locations of these components resulted in the plane's CG being where I wanted it. The spreadsheet is built around this formula, which determines the overall center of gravity of a collection of many individual pieces. To calculate the overall CG, you take the weight of each individual piece, multiply it by the distance of its individual CG from a reference plane, sum up all those products, and then divide by the total weight. The resulting distance is the overall center of gravity, or where the collection of pieces would balance. I started by listing the individual airplane parts and batched them into subcomponents. In the case of the nose, it consists of the pitot tube, 4 frames, and then the upper and lower skins. Next, I calculated the weight of each individual part. Depending on its material, the weight is determined differently. The pitot tube is 3D printed, so I used the slicing software to tell me the weight directly. For the frames, I used Fusion 360 to tell me the volume of the part, then I multiplied by density to get the weight. For the skins, fiberglass cloth is characterized by its weight per unit area, so I measured the surface area of each skin, then multiplied by the weight per square inch. I multiplied this value by 2 to consider the weight of the epoxy that laminates the skins. Then I used Fusion 360 to tell me the CG distance from my reference plane to each part. Lastly, I multiplied the weights and the CG distances. I repeated this process for all the parts I included in my Fusion 360 model for the plane. This gave me all the data I needed to estimate the total airplane weight and the sum of all weights times CG distances. Then I just plugged everything into the equation I showed earlier to get the overall airplane CG. Okay, great. So I have the total weight and the CG location. How do I know this isn't too heavy, or that the CG location is suitable? Well, somewhat coincidentally, Motion RC and e-flite make RC F-16s of the same scale that have been around for a while and are tried and true in their flight performance. Their manuals list weights and CG locations, so I was able to compare my values to those. Motion RC has a version of the plane listed as heavy as 2,400 grams, and e-flite lists theirs at 2,090 grams. It's not clear if these weights are with or without the battery, but assuming they are, my estimated weight is between those two, so this gives me some confidence that my plane won't come out too heavy. For the longitudinal CG position, Motion RC recommends 90 mm from the leading edge of the wing at the fuselage, and e-flite gives a range of 90 to 110 mm. My calculations are estimating that my F-16 CG will be 96 mm aft of the leading edge at the fuselage, so again, pretty close to the values of the other planes. If you're building a custom RC airplane and don't have other airplanes to reference, you can find easy-to-use RC airplane CG calculators online to help determine a good starting point for the CG. Another benefit of this spreadsheet is that it gives me target weights for each subcomponent that I can compare back to after I build each of them in real life. This gives me the ability to make corrections to my build along the way and prevent me from running into the scenario where I finish the entire plane and then find out it's way too heavy. It's always easier to add weight later on than to remove it after the plane's built. So far I've built one horizontal stabilizer, most of the vertical fin, and the removable portion of the lower fuselage. Let's see how their weights compare to my estimates. My spreadsheet estimates the lower fuselage portion should be 45.9 grams, and the actual part is just under 50 grams, so a little bit heavier. For the horizontal stabilizer, the spreadsheet is estimating 33.3 grams, and the actual part is 38 grams, so again a little bit heavier. And for the vertical fin, my spreadsheet is estimating 46.9 grams, and the actual part is 57.9 grams, so quite a bit heavier. Okay, so unfortunately the parts are ending up to be a little bit heavier than my estimates, but then again, that's not too much of a surprise because my spreadsheet, again, is just an estimate and it doesn't include every single part that is going to be on the airplane. For example, on the vertical fin, my spreadsheet isn't considering the hinges that I have inserted, so those add a little bit of weight too. But I think the biggest contributor to these parts being heavier than my estimates is the epoxy that I was using to bond all the internal structure to the skins. In the spreadsheet, I didn't have anything to compensate for that. For the horizontal stabilizer, I think a contributor to it being heavier is the fact that all the primer stuck to the skins after it released from the molds. So I think that's adding a little bit of weight too. But going forward, I'll make sure to weigh each part as I build it and make sure it's not too much heavier than the estimate. What I'll do for the next subcomponent as I build it is weigh all of the individual parts separately before I glue it all together. For example, I'll weigh all the balsa parts separately, I'll weigh the fiberglass skins separately, and I'll weigh the birch plywood parts separately. That way I'll really be able to pinpoint where the extra weight is coming from. If you'd like to learn more about aircraft weight and balance, I left a link to the FAA's Weight and Balance Handbook in the video description. Thanks for watching and see you next time.